All right, everyone, good morning. Hello. Pay attention to me. Hi. So this morning we have our REACTO talk on data structures. Oh, so I'd like us to begin, I'd like you to begin by sorting these into abstract data types and sort of concrete data structures. I'll give you, we'll have like 5 minutes to do that. Oh, sorry, sort these into abstract data types versus concrete data structures, which I know we have not gone over that distinction, so part of this is pondering that distinction for yourself and letting me finish my meal.
Oh, you're so kind to bring that. Thank you. You have to pay a co-check fee?
Yeah, I sort of intentionally did not define abstract versus concrete. So take your best guess, and we'll talk about the definition of those things. But basically, sort them into two classes, one of which is more concrete than the other.
As an abstraction, it's not like a
No, I think it's just like
No, just
one
separating one from the other.
Yeah. So I would think that all of those things like array, list, graph. Well,
what's wrong with the list? The list is an array. A list is an array. I know, therefore.
A list is like, I've never used it.
So what do you do?
I actually like, so I like family from City, so I just like had to do, so I basically just like
Define.
Oh, really? I didn't even really get it done, to be honest. I was just like looking at it on it.
That's about the hash.
I feel like hash will reach.
Yes. Reduced further. Yeah. And therefore, list is just an array.
What do you think? Do you think so?
I have no idea. I would say it was math.
Would a hash be not be right? Because you said you completely define a value.
No, and after data type is something else.
Oh, really? Okay.
Yeah, I don't think existing in JS.
Probably like
All right, is anyone still working or want more time? Okay, let's talk about these. Let's see, shall we talk about this distinction or classify them and then see if the distinction emerges? Let's talk about the distinction a little bit beforehand. So when I say abstract data type, ADT, versus concrete data structure, what do I mean? Someone want to take a stab at that? Yeah. Yeah. And then a data type, the abstract data type. Yeah. So this is like the interface of operations. What can we do to this thing? And then the data structure is the implementation. How do we do it? Which means that a data structure will implement an abstract data type. Sorry, was there a question? Okay. So with that in mind, let's walk through these. What is an array? Sorry? Discrete? Like, sorry, like a data structure? Yeah, so generally we would say this is a particular implementation, like especially if I said like a C array, this would be an implementation of what? Yeah. What about tree? Yeah, a tree is abstract. There are many, many different ways we could implement a tree, which we're about to talk about. What about a binary tree? Also abstract, yeah. It's a more specific abstract data type than a tree, but it's still abstract. There's still a bunch of different implementations we could provide to it. List, we already said was abstract. I maybe didn't shuffle these very well. Stack. Yep. Graph, I did this very badly. Yeah. Hash table. So an array was a concrete data structure, and it's maybe a little bit vague what we mean when we say array, because if we mean a JavaScript array as specified by the JavaScript language specification, that's actually an abstract data type. It does not specify how the various operations are implemented. So the JavaScript language spec says an array must be able to look up items by index. It must be able to do like an index of, map and reduce must be defined on it. And it tells us the maximum, like the worst big O of those operations, but it doesn't specify how they're implemented. And so the arrays that we're familiar with are technically, I mean, they definitely have a concrete implementation that we've been working with, generally V8s, but they are specified as this abstract specification in the JavaScript language. What is? It's a data structure, a concrete data structure, rather than an abstract data type. That is, if by array we mean a lump of memory that we can access individual elements of by adding to the address of the start of it, which is what we mean when we say C array. That defines a way that we might implement a list. Okay. What about hash tables? Yeah. So this is a data structure. What does it implement? Yeah. So map is the abstract data type, or object. Like JavaScript objects are basically maps with a bit of weirdness. Adjacency matrix. Yeah. Implementing what? Yeah. And we'll talk about what this is exactly. Queues? Yeah. We implemented one way back in the first workshop of junior phase, and that was a concrete implementation of this abstract data type. Maps, we already said, were abstract, and then linked lists. Yeah. it's a concrete data structure. Linked list implements what? List. You can, or queue, right? You could use it to implement a queue. That's true. You could use anything that implements list to implement a queue, because a queue is a list with some operations removed. All right. So let's talk about some of these in their abstract cases, and then we'll talk a little bit about the specific implementations that we might choose and what implications those implementations have. So lists, I previously prepared some notes, so we're going to go through these. So lists support generally appending, removing, and inserting something at a particular index. That's probably the largest set of operations a list can be said to support. And you can also get an item at a particular index and generally get the size of it. You can always, for a particular problem, you can always say, like, suppose we have a list that does not support the count operation for some reason. But generally, when people say lists, this is the scope of operations that that you're generally talking about. And we already said that this is implemented by, you might implement it with an array. So if we talk about an array that implements a list, we're talking about a contiguous block of memory somewhere. You hold onto the address of the start of it, the size of the block, and maybe the number of things in the list. And then the idea behind storing a list in an array is that you store item n at the position, or at the memory address start plus n times item size. And so you use that to implement get and set, and then you store this size elsewhere and use that to figure out how many things are in the list. With this implementation, what are the big O's of these operations? So let's actually start with retrieval, because that's a little easier to reason about. So if I've implemented a list with an array, what is the big O of retrieval? 1, what? And if we don't, yeah, so instead of storing the number of things in the list, I might have stored a sentinel value at the end of it. So this means that I would store, for example, if I have a list of characters, I might store HELLO and then null. And then I might have like 10 empty spaces, which aren't actually empty, they just have garbage, at the end of it, because my memory block is bigger than the number of things in the list. Does that make sense? So the size of the block is not necessarily the size of the list. The block might be much bigger, and we either store the number of things in the list separately, or we store some special value that says I am at the end of the list. And if we've stored this special value, then yeah, now count is O of n, because we have to go look for it. I can't type sentinel today. Why would we do this? It just kind of seems worse. Yeah.
Because if we predefine it inside the array and we don't want to use the entire array, or we made later, the Sentinel will prevent us from using the entire array, which may be worse than overman.
Sure, but we could have stored the count separately. So we could have just over here been like count 5. Or if we want, we could say, okay, the first thing in the memory is going to be the number of things that follow it in the list. Those are basically equivalent ways of handling the count. And then we wouldn't have to scan the whole thing. Yeah.
It's a little bit more costly to update the count for every insertion.
Yeah, it's a little bit more costly. Even that, now that I'm thinking about it, like if I insert something, I have to write there. I have to write like X there, and then I have to write another null value, like another sentinel. If I'm storing the count, then I would have to update this, and then store the count, or update the count. It's like not clearly better, except that maybe it's a little faster to change the value here and then change a memory address right next to it than it is to change a memory address at the beginning of the block and then change something at the end of the block. Yeah.
But if you have the count, then you know immediately where to go to get to the end. And it should be quicker than not counting to the end. You immediately go straight there. You know
Yeah.
the operation to do.
Yeah. So I was hoping we would come up with some like really great reason to use a sentinel value, and I actually can't really think of one. One reason in this particular case, if we're storing characters, might be that there's actually there's a Intel, or like an IA64 in the instruction set that all our processors use. There are special instructions to handle dealing with arrays of characters that are null terminated. There's like special instructions that tell the processor to seek to the end of this null terminated character string, and so on. You might guess that this is because C decided to store characters in this way, and you are correct. Or to store strings in this way, and that is exactly why. So there's a certain argument from it's what everyone else seems to do, but I think actually in general, just storing the count is probably a better strategy. Yeah.
Because after comparing two strings, it seems like it'd be easier to compare two strings that an initial character and check their.
Yeah, so it does kind of make looping over a string like easier in some sense. Like if I have two strings, I can scan a string just by doing a while loop until the character I read is 0, and I can advance 2 pointers along these strings, comparing them. Like the code to do it is pretty easy. It's something like if P isn't Q, return false. Otherwise, down here we'll return true, and something like that. So that like makes string. Sorry, this is C, not JavaScript. C in what Ashi remembers of C. So this is like maybe more straightforward than having to look at the lengths of 2 different strings and make sure that the index that you're keeping is not growing larger than either of them. I don't know, though. Given how many buffer overflow attacks there have been, which specifically depend on the code accidentally not writing the sentinel and thereby making the string much, much longer than it should be. This is like one of the most common security vulnerabilities in the world today. I think this was the wrong decision to use a sentinel value. So, when you're designing your list data structure, keep that in mind. Okay, so O of 1 for get, O of 1 for count, probably O of n, or probably O of 1 if we do things that way. What about these operations, append, remove, and set? Why is that? Oh yeah. So the answer was constant time because we don't have to move stuff. So my question then is, what if the block of memory looks like 1, 2, 3? So there are 3 slots in the block, and they're all full, and I call append. Right. And presumably then copy everything into it. Right. So then it seems like it's O of 1 sometimes, maybe even often, but then O of n sometimes. How, here, I'll say, but O of n if we do. So how can we talk about that? Yeah. Yeah. So say a bit more.
So it's basically saying on average it will take this amount of time. So in this case it would be on average O of 1.
Yeah.
If you implement a strategy where you double the array.
Yeah. So exactly. So the answer is that we can look at, like, in general, how long does it take? Specifically, we can say that, well, occasionally it's O of n. Usually it's O of 1. So we can take this cost and amortize it over all of the times that it's O of 1. And if when we need to push an additional thing onto the array, or an additional thing into the list, if we only ask the operating system for 4 memory blocks, so let's actually draw the blocks, or for a block of memory that contains 4 things. So if we go from this state to this state, then I think the next time we add something, we're going to incur another O of n penalty, because we'll have to copy all these things to another list. And so in that case, it would be O of n, which would be bad. We would like for append to be cheaper. So instead, what we can do is, whenever we hit the end of our memory block, so in this case, we've appended 4, we're going to ask the operating system for twice as much memory as we have now. So we're going to double our allocation size and put a 4 in it. And then we know that these 2 are empty because we're storing the number of things in our array as 4, or the number of things in our list is 4. And then when we append 5, we still have space, and when we append 6, we still have space. And you can do sort of a more formal proof of this, but you can kind of look at it and be like, well, for every time that I append something and have to grow the array, that's an O of n operation. And if I cut up that operation and ascribe one slice of it to everything that is currently in the array, that makes sense? Like, it's taken, let's say it's taken 3 seconds to do this. If I ascribe 1 second to each of the 3 things that were already in the array, it's as though each of those just took twice as long. And since each of those took O of 1 time, my append is amortized O of 1 time. If that logic is a little bit fuzzy, that's okay. The general takeaway is, if you're smart about how you, if you have like an occasionally expensive operation, you can be smart about how often you make yourself do it. Generally, and this is generally the approach, is to double whatever you were, whatever the capacity that you had before. Then you'll be able to take an occasionally expensive operation and basically turn it into an operation that on average is cheap, relatively cheap. Yeah.
So if you know that you're going to continue to push into your array to double the size, it's better to double it right away and then you push like double its size and push it in afterwards? Or?
Well, the special thing with doubling is that you know that you won't have to do it again until you've pushed in as many items as are already in the list, which means that the OFN cost of pushing those things into the list has basically been spread evenly amongst the things already in the list. So you can claim that it's a constant time insertion, even though it's, in sort of a very literal sense, extremely not constant time. It's like usually very, very fast and then occasionally extremely slow.
But how would you implement that?
Yeah, so we have, we're storing the number of things in the list, the start of the memory allocation, and the size of the memory allocation. So if the number of things in the list times the size of things in the list equals the size of the memory allocation, our container is full, like our buffer is full, and we need to grow it. So at that point, we're going to go and request from the operating system a buffer. We're going to allocate some memory with the malloc function. And we're going to ask for 2 times the current buffer size, or 2 times the current number of items in the list times the size of an item in the list. Okay. Any other questions? We've gone probably one step deeper into this than you need to, but I'm actually glad we did because this is the kind of analysis that you sort of want to do on your own time with all the data structures you encounter. Is like when you learn an implementation, understand some of the details about why we say that the time complexity of these operations are the way they are, and how does the underlying memory, how do the algorithms operate on the underlying memory? Okay, removal, big O.
Could be OFN, right?
Why would it be OFN?
I guess, what if you remove like something at the start of the list and you have to shift everything?
Yeah. So if you remove something at the start and you don't handle it in some other way, you could imagine having some way of tracking holes. Then yeah, you have to do a bunch of copying. So that could very well be OFN. Yeah. If you don't have some sparse methodology. And by sparse, I mean some way of saying like, oh, this, we have like these, we have like 20 things, but they're scattered throughout the array, which is actually kind of hard. That is at that point, a different data structure than the one we've described. Good. And then set is OF1 by the same logic as get. It's just literally one additional instruction. Okay, cool. Linked lists, of course, also implement arrays, or also implement lists. Let's talk about those instructions without going into quite as much depth. I think you might remember this from junior phase. List. Sorry? What's append? Yeah. Otherwise, you have to find it, so it would be OFN. Removal. Yeah, it's OFN. Why is it OFN? Yeah, to find the index. But there's another operation that linked lists might implement, which is like remove. Really, it would be list, but remove this node, which is OF1. At that point, you already have the node. Set on an index by similar logic is O of n. And again, if you already have the node, then of course it's O of 1. Retrieval is O of n, and count is also O of n. So this just looks strictly worse, right? Except for one, except for one operation that we don't have here, which is splice, and also for removing a node. So the moral of the story is that with linked lists, if you have a pointer to the node, it's easy to do edits around there. If you're trying to access a node through an index, then you'll generally have to scan the list for it. There's again data structures that can make that process faster. Like you can store a skip list, which says if you're looking for index 5000, start here. This is index 4500. I would imagine so, but I don't know. In JS? That's something you'd have to benchmark. I don't know if you could infer it from the language specification. Oh, sorry. Yeah, so the question is splice faster than 2 slices? It definitely creates less garbage than 2 slices. Yes, in the sense that if I was doing an operation, if I was editing an array in such a way that I could use splice, I would use splice. I might not use it like on a whiteboard in a whiteboard interview because there's a decent chance I would get the arguments wrong. It's not particularly readable, and in a whiteboard interview, I could be like, here, slicing and ... notation, and I'll hand wave that splice is probably a better way of doing it, but probably the interviewer doesn't want to see that anyway. But it does create less garbage demonstrably, right? Because with splice, you mutate the array in place. With slice, you have to create 2 slices and then generally copy those into a third array. So you've already created a couple of garbage arrays, even if the JavaScript engine is smart enough to avoid doing the copies, which it honestly probably isn't. Like, you could imagine that making a slice of an array you could imagine an implementation where it doesn't copy the underlying elements until the sliced array is written to, a sort of copy on write methodology, which maybe it does, but that also sounds like a lot of work. And copying memory is, in general, somewhat cheap. Wait, how else do you do the things splice does? No, but that doesn't do the thing splice does. That creates a different array and copies everything into it. But if you want to mutate, you're right, JavaScript doesn't generally create a bunch of methods. That's why there's one method, splice, which handles all of the in-place operations you can do to an array. JS arrays are mutable data structures that are editable in place, and there's a performance reason for that. Like, it can be faster, both due to garbage collection pressure and due to the fact that you're not forcing additional allocations or copies for that matter. It can be faster to edit an array in place. And so for operations or in places where performance is important, or in any code where you're about to push it to production. If you're sort of sketching something out or like making demonstrative code, making a whole bunch of copies is fine, but at some point you start to care about performance even a little bit. And then if you are editing an array in place, you would prefer to use splice. Otherwise, you can't do things like implement a sort in place at all. That's not totally true, but it's much less efficient. Who slacked everyone? Okay, that's fine. Okay, let's go through the rest of these somewhat quickly. So maps and sets are another abstract data type. They are sort of two sides of the same coin. A set is a map which has no values. It has only keys. Another way of thinking about this is the values are always like true. I am in the set. So operations on maps are generally set a item for a particular key, get the item associated with a key, and tell me how many things are in this map. When implemented with a hash table, these are all O of 1 operations. Again, you can sort of think like a hash table is ultimately an array, which means if the map can grow as much as we want, then at some point we'll probably have to make a copy of the underlying array, which will be an O of n operation. But again, we can say like, okay, we'll be sort of clever about how often we do that to guarantee that these are all O of 1. Objects are maps in JavaScript. Objects have a little bit of extra stuff too. They have a prototype chain and property descriptors and so on. But in general, you can think of an object as a map. And JavaScript also has the map class and the set class, which implement maps in kind of a more traditional way. So why is it even possible that my terminal takes 3 seconds to start up? So you can create a new map and then say set a key on a map. Hello. And then get it. Maps, when used as object, or the map class has the ability to use any object as a key. But this probably doesn't work the way you think it does. What do you think happened there? Yeah.
Did it convert the key to a string?
No, the key is actually the array. Yeah.
Is it because like the place in memory of like what you originally set it to is different than what you're calling it with?
Yeah, exactly. So when you use objects as keys in a map, the map uses object identity as the hash value. So what that means is if the key you're passing in the second time wouldn't compare triple equals equal to the first to the object that was used as a key, then you won't get the same value. So I can, now that I've created this array and stored it as a value, I can set something here, another array. If I look at the map, this is confusing as hell, right? It looks like we've got 2 different values for the key 1, 2, 3, but actually we have 2 different keys because these are technically different arrays. And now I can get and I will get another array back. So you can use objects as keys in maps, but it is maybe not as useful as you would hope. Yeah.
If you set an object the way you did at first, is there any way then to access it?
Presumably there's like m.keys. Oh, yeah, so yes, you can iterate over the keys and get the appropriate key. Yeah.
But if my memory serves me correctly, sets are not guaranteed in order, so that's not exactly best practice.
I mean, you would, yeah, like, how would you even know anything about this? Like, how would you know which key you want? Of like all the keys in
And
there.
what I'm saying is, like, my understanding is maps don't have a certain. There's no set order, meaning in theory, anytime you run it, the order might change.
Is that true of JS maps? It varies. Let's see. JS map iteration order. Okay, I'm gonna guess that it's in order of insertion, and that's defined.
Based off of my use of maps, that's how it works.
It will only map to the object's insertion order. Wait, which is random? Wait.
Well, it depends how you're setting them.
Yeah, a map object iterates its elements in its insertion order. So it is actually deterministic, and you could do this, but why on earth would you want to? I mean, if you're inserting things into a map and using keys and then looping over those keys later to get them out, what you actually wanted to use was a list. Like, if you just want the second thing you inserted, just push them into a list and then get the things out of the list. Okay. Any questions on maps or sets? I feel like we use maps an awful lot in JS. And so that is, we use objects, which are maps. So they are easier for us to reason about. Yeah.
I mean, just like how often would we use like hash tables since we have objects?
Well, every time you use an object, you're using a hash table.
But like
explicitly?
Like, yeah, I guess.
I mean, since you have the map class and objects, you probably wouldn't like write your own. There would have to be some really compelling reason to get you to do that. On the other hand, maybe you find a compelling reason. Like maybe you get into GPU programming and you need something like a map, but stored in a texture and accessed by a shader. And so then you find yourself writing a hash table that runs on the GPU. This is a thing you might do. Maybe later. Okay, so those are maps. Sets just don't have the values. So you can just use a set to check and see if something is there. I think it's add. This is useful in certain algorithms when you're keeping track of all of the things you've seen, for example. All right. Here's one of my favorite data structures because it's cool. A trie is a map of maps, or if you like, it is a tree in which each node is a map. So this is where we start getting into interesting compositional data structures. The reason we might use a trie is because another word for it actually is the prefix tree. So each node within a trie contains all of the words in a language or in a data set that begin with a particular prefix. So if we look, here's an example of a trie. Here we're using just JavaScript objects as our maps, which is fine. And we're imagining here that we want to store a dictionary in such a way that we can look up elements by prefix. And so we might, in inserting the word Surabi, we start from the empty, from an empty object, and we look for S. We don't find it, so we insert a node for S containing the empty object. And then we do the same thing for U. and then we do the same thing for R, at each level going into the node that we've just created, until finally we get to the end and we store the entire word as sort of a marker to say there's a word here. So if we insert another thing, let's say we insert Sean, oops to that, and oops to that. My data is a little bit noisy. So if we insert Sean, then we visit the S node, and then the S node will have two children. So one child is U, and that stays unchanged. And then the next child that we insert now is E, which has a child A, which has a child N, which we mark as being a word. So now if I want to find all of the words that start with S, I just visit the S node and traverse the entire tree and collect all words. Yeah?
What if there's repetition of
Then you just keep going deeper. So like, I'm trying to come up with an example that starts with S. Or if I insert ja, ja, ja. What's that?
The level of nestedness always reflects the order of.
It's just the length, yeah.
Yeah.
Yeah. If there's a word that's 100 letters long, then the tree will be 100 things deep at that point. Generally, the tree is relatively well behaved because English words and words in most languages, well, English words aren't that long. If you have a German try, maybe it'll end up kind of deep and possibly encountering some pathological tree case. But again, like a tree that's 200 levels deep is sort of deep for a tree, but not that deep. It's not like too deep to use a recursive algorithm, for example. A tree 30,000 levels deep might be, but I don't think there's a lot of languages with 30,000 letter words. So this is useful for, it's a useful way to disassemble words or any kind of string if you want to do searching on it. So you could use a dictionary like this for prefix searches. You could use a dictionary like this for solving Boggle, for example, because at any given point, the word that you're trying to evaluate is yours at some node in this tree. And all of the words that could follow are children of where you are.
And then, like, so what kind of search, if you're actually doing a lookup, do you do like a breadth first search, or like how do you actually go through it?
Usually you're searching for a particular word in a try. In any case, if you are searching for a particular word, then you are just walking the tree. So if I've typed in soba and I'm searching for it in this try, then I'm going to look up the S node. I'm going to look up, so it'll be that dictionary. I look up S, which gets me everything under S. And then I look up O, which gets me nothing. And so I know that by the time I get there, there's nothing in the tree for it.
And so if you're actually at S, to see if there is an O node, do you have to look at every child node to S?
No, because it's a map. So it's O of 1. I just look up. Or, I mean, literally, it could be this JavaScript object, and then it's really just like P of letter. Yeah. Okay, any questions about tries? They're a slightly exotic data structure, but we mentioned them because they might be useful, I don't know, tomorrow.
That's how autofill would work, like if you start typing and it's
Yeah, definitely for a basic autofill, you could find all words at least that start with my prefix. You could also imagine a try made of words rather than letters, and then you could complete phrases. I think like Google's auto search is obviously doing something more clever, but you could make this into a more clever data structure. Like maybe here I store a probability value that says if you've gotten to this node, this is the probability that the word you actually want is strawberry versus something deeper. In this case, it would be 1, I guess, because there's nothing deeper. But here I could be like P. So you can be, depending on your use case, you'll adapt these data structures to what you need and store possibly more data in them. Okay. So for trees, trees are sort of a large class of data structure. Anything with nodes where every node has at most one parent and 0 or more children. And what falls out of that is that there is a single root node from which the entire tree stems. Because every node has at most one parent, so at some point you get to a node with 0 parents, and that's the first one. So we can do a bunch of things with trees, generally by applying additional constraints to them. So if we, famously, we might define a binary search tree as, first of all, a binary tree, which would be a tree where every node has between 0 and 2 children. And also the left child is less than or equal to the value of the self node, which is less than or equal to the value of the right child. So with those additional constraints, the binary constraint and the ordering constraint, we get a binary search tree, which, as you'll recall from junior phase, lets us do fast lookups on a particular value within a data set. There's a whole bunch of other kinds of search trees. So there are like trinary search trees. There are B trees, which are a generalization of search trees where each node can contain some number of children, and the number of children kind of varies depending on the performance characteristics you want. B trees are actually, I think, the most commonly used tree searching data structure in databases and file systems and so on. Mostly because if you have a B tree, you can get all the performance of binary search trees, but you can also potentially do much better because instead of just cutting your data set in half with every level, you can cut it down by thirds or by quarters. There's obviously a consummate increase in complexity, and it's possible to pick the tuning parameters of your B tree wrong so that you actually end up worse. And this is a kind of common trade-off. You will often see that there's a basic data structure that works sort of generally well for many problems, and then there are more specialized versions that require more effort in some sense or add more complexity, but can provide better performance. Another one of those is the red-black tree, which tends towards being balanced. It adds an additional bit of information to each node, namely whether that node is red or black, and then adds a bunch of constraints with regards to what nodes can be children of what other nodes, and what happens if you need to insert a red node under a black node, or this or that. And if you obey all those constraints, then you get a tree that is generally balanced, which means that you avoid this awful scenario where your tree has just become a linked list. And instead you tend to get these runtimes rather than these, logarithmic rather than linear runtime. Again, I mentioned red-black trees, not because they'll be useful this week, but because they come up now and again in interviews, and even if you don't have the ordering rules for red-black trees memorized, as I definitely do not, it's maybe good to like have read them once and be familiar with the fact that they exist. Any questions on trees? Oh yeah, what are some data structures that implement trees? Sort of technically. I mean, linked lists implement lists, which you could say a list is a kind of tree with the additional listness constraint that a node has 0 or 1 children, but I don't want to do that. What's that? Yeah, so then you have the linked tree data structure, which is very much like a linked list. Yeah, so linked tree. Any others? Yeah. How? Yeah, so if you declare that the children of the element at I are at 2i and 2i plus, is it 2i plus 2? It's 2i plus 1 and 2i plus 2. Then if I have, let's say, this data structure, this tree, then I can store it in this array. So I'll have 3, 4, 5, 6, 7, I think. Let's check that. So the children of 3 are 4 and 5 at 1 and 2. The children of 5 are 0, 1, 2. They're at 5 and 6. So 0, 1, 2, 3, 4, 5, and 6 are null and null, so that's correct. This is a child of 4. And then the children of 4 are, this is 0, 1, they're at 2 and 3, which looks true. Oh, wait. 0, oh yeah, at 3 and 4, which is right. What's nice about this? Yeah, constant time access for a node, if you know that it's there. It's easy to copy. You don't have to traverse a whole bunch of pointers. If you just know how big this memory block is, you just copy the memory block. Also, if you are implicitly storing them in breadth first traversal order, which is both nice for output and depending on what constraints are on your data structure, you might get them sorted. So in fact, there's a sorting algorithm which basically says define certain constraints on a tree, insert everything into that tree, and store it as this array. And if you look at the array is sorted. It's like a little magic trick.
What's that called?
Is that heap sort? Do you remember? I think it's heap sort. I'm pretty sure that if you look up heap sort, that's what you get. Because this is definitely a canonical way to store a heap. A heap, which is the kind of tree, not the heap, which is the place where everything in memory lives. The heap is called the heap literally because it's the pile of crap sitting in the corner of the room. That's the kind of heap you're supposed to be thinking of. There's also the heap, which is a kind of tree, which is a binary tree with certain ordering constraints. I don't know why you would name even one thing a heap, let alone two, but that's what we've done. Okay. Trees are very useful. A huge number of data structures in computer science are trees of one kind or another because of this logarithmic quality, where if you can organize something hierarchically, then you can sort of quickly find things stored deeply within them while discarding a lot of the data set on your way down, which is great. However, trees do not capture how the natural world works in all cases, which unfortunately means to model many real-world systems, we need graphs, which are probably the most unwieldy data structure we have. Who can define a graph? real fast. Yeah.
It's like a tree that has multiple parents. Like you can, it's not just there's cycles. Like
Yeah. So so it's basically what we said about a tree, but without any of the constraints we said about a tree. So you have nodes which can be connected to other nodes, and as far as being a graph is concerned, that's basically it for constraints. We can talk about different types of graphs, though. Let's see, yeah, here. So a graph has, we typically call them vertices and edges. Those are the names of the nodes and the connections between them. We will talk about directed graphs and undirected graphs. In directed graphs, the edges have some direction. In undirected graphs, they don't. So Git is one of the canonical examples of a graph. In Git, are our edges directed? Ben's nodding. Yeah, so they are, because this commit, for example, references this commit, but not vice versa. And you can decide which way you want to conceive of the direction as flowing. Generally, I would say it's down, along with the arrow of time. So because of time, there's sort of a clear directionality in Git. We might also say that, or we sometimes also talk about graphs as being cyclic or acyclic. So an example of a cyclic graph is this one, where we can go from A to B to C all the livelong day, forever and ever. This more complicated graph is acyclic, because there is no way, once we have left a given node, to return to it. All edges basically flow away from a node. Git, in particular, is acyclic because, again, time only goes in one direction. You can't make a commit that was both after and before another commit. That would be really impressive. If you can, I want to see it. And that makes it a directed acyclic graph, which is a particular kind of graph. It's basically a lot like a tree, except for the fact that you have these merge commits in the case of Git, which have two parents. So directed acyclic graphs, because they're tree-like, are a little bit easier to work with than sort of general case graphs. So you'll see in algorithm discussions, you'll see algorithms that can operate on directed acyclic graphs, or certain operations that are easier, mostly because you don't have to worry about maybe running into a cycle. On graphs in general, the most common thing you'll be doing once you've turned something into a graph is searching it, is like searching for a path between point A and point B. And there's a bunch of algorithms for that. Nodes in a graph. You already know a couple, even if you don't know it. You can sort of guess at a couple of ways of finding a path through a graph. Yeah. And which one of those would we prefer? Yeah, why? I think they both will find all paths. Yeah, so BFS is preferable because it's generally faster. That's kind of surprising because with trees, we say the depth first search is usually fine. They're both usually OFN. And indeed, these are both technically OFN. But if your graph is very large, BFS, doing a breadth-first search, will exploit the fact that your destination is usually kind of around where you started. Whereas depth-first search will literally run down the first rabbit hole that it finds as long as it goes. Depth-first search is, like, breadth-first search is my thought process when I'm being careful and taking notes and sort of making sure not to get too into something. Depth-first search is my thought process when I'm high. Like, I will get on some random rabbit trail and go. So in general, when you have a large graph to search, breadth-first search is the way to do it. Go, because your destination is probably close rather than in Iceland. And a specific kind of depth-first search, or breadth-first search, that's very commonly used is Dijkstra's algorithm, which does a breadth-first search of the graph and does it in... Actually, I'm now having trouble remembering what exactly makes it different. It uses a priority queue, I think, to ensure that it finds better nodes, better paths faster. Kind of BFS priority queue. Ashi needs to review this. This is probably the most common scan a graph to find a path algorithm that you'll see. It ends up finding a path, the lowest cost path to all nodes from a given start point. Another algorithm for searching graphs that you'll see is A*, which requires that you can describe a heuristic such that the heuristic will always overestimate the distance. Will always hit exactly or underestimate the graph distance between 2 points. So this basically means you need to be able to say, given 2 points, not knowing anything about the graph between them, what is the best path that you could possibly find. So for that reason, A* sees a lot of use in literal path finding and like finding your way around 2D or 3D space, because we know such a heuristic, and it's the Euclidean distance between 2 points. Like, you're not going to do better than that. There might be a wall there, so you might do much, much worse, but the requirement of A* is that you just can't do better. And then there's some extremely exotic data structures that we're not going to go into. You can look up Bloom filters if you like. They're useful in a very small subset of circumstances. Okay, so we will see problems about, I think, all of these throughout the course of the week, and if we don't get to one, I think there's a problem thrown in the last week. These are the foundational data structures for a lot of interview questions, and honestly, a lot of the harder problems you encounter in computer science. So, especially as senior phase winds to a close, and you start to spin up on really practicing for interviews, these are what I would recommend starting from, and then go and dig into stranger exotics later. All right, today we have code reviews. I believe your fellows have made appointment slots for those, so we're going to start them at 11. Until then, you have like 20 minutes to get those last pull requests in, do any code reviews, and sort of get on the same page. We're going to try and have these be a little bit more guided by you. So your fellow is going to be driving, but also have something a little bit more to walk us through, and come prepared with any questions you have for Gabe or I. Any last questions? Okay, great. Best of luck.